Welcome everyone to the 42nd Derby Lecture Series featuring Professor M. Stanley Whittingham, the 2019 recipient of the Nobel Prize in Chemistry. So thank you all for coming. So this event is organized by Chemistry Graduate Student Association, and this event has been held for 4 decades by graduate students, and this event is all the events surrounding the Derby Lecture Series are organized by graduate students and also graciously funded by several sponsors. Our biggest sponsor is Clariant, who has been sponsoring us these events for many years. So I would like to thank Clariant and the graduate students for organizing these into success. Now I would like to give a brief introduction to our speaker, Professor Whittingham. He is originally from Nottingham, England. He received his BSc, MA and PhD from University of Oxford. Now he is a distinguished professor of chemistry at Binghamton University, State University of New York. He serves as a director of Northeastern Center for Chemical Energy Storage at the US Department of Energy at Binghamton. He was awarded Nobel Prize in Chemistry in 2019 along with Akira Yoshino and John B. Goodenough for the development of lithium-ion batteries. He has received many awards and honors, just to name a few. In 2015, he received Thomson Reuters Citation Laureate, and in 2017, he received Senior Scientist Award from the International Society for Solid-State Ionics. In 2019, he received his Nobel Prize. So we are delighted to host Professor Stanley Whittingham for these events, including the Kentucky Derby, and thank you for joining the exclusive group of University of Louisville Derby lecturers. Please join me in welcoming Professor Whittingham.
Thank you very much. I hope you can hear me okay. Yep. Good. So I want to give a bit of a, I won't call it chemistry free talk, but almost chemistry free talk. But as they say, if you came yesterday, coming today, you'll pick up just that bit more. So we say it again, and in the end, you'll get it. So just raise your hand in the audience if you do not have a lithium battery on you at the moment. Is there anybody who's willing to? No? So we asked the same question at the Nobel ceremony. The only people who didn't have them were the royalty, because they don't carry them with them. But everybody else had an iPhone or something equivalent. So what I want to really show is some of the issues with climate change and what we need, in fact, to have a clean economy, an environmentally friendly economy. So let me move on and just show you a few examples, all from the last 6 months. You'll recognize some of these. In the top left hand, that is Germany. Beneath that, you may recognize that is Kentucky, okay? And the center, that is the Victoria Glacier in Banff National Park. When I first went there about 20 years ago, that whole valley was full of the glacier. You can just see it now in the remote distance. On the top right-hand side is Santiago, Chile, and beneath that is near Boulder, Colorado. I say all within the last half of last year. So these are some of the things that are happening because of the climate change. And I don't call it global warming, it's really global messing up. It's making extremes on both ends. So we really need to address that, and I want to touch on a few things today. And without getting into too much of the chemistry. So I gave a talk to the Senate in Chile beginning of this year, and they wanted to know, how does humanity get disrupted? Most of you are too young to remember the last disruption. That occurred when you got iPhones, laptops, where you had immediate communications throughout the world. You didn't have to rely on the newspaper or the TV or anything else. So that disrupted all your lives, and you now know what's happening in the world within seconds of it occurring. second major disruption, we're still getting over it, and that's COVID. So that's a bad disruption, but it had some positive aspects. We learned we can make vaccines very fast. We got those skills. We learned in the negative sense that global supply chains are not a good thing. We've got to have our own supply chain. And what we're now worrying about is the whole climate issue, and I want to emphasize, particularly to those, can I call them young radicals, who say we want to get back to where we were. We're not going to reverse climate change. What we can do at this stage is stop it getting worse. Just because the population is increasing, it's not going to be, in my mind, feasible to take CO2 out of the air, say, in this building. We can take CO2 and methane out of the sources where they majorly occur, which means taking all the internal combustion cars off the road, stopping burning oil and coal to make electricity. We can do that, and that will make a big breakthrough. So the issues we have, renewable energy, you have some of it in this state. Solar and wind are intermittent. It means you've got to store the energy for when you want it. And this is a huge issue right now in California. They're making far too much solar in the middle of the day, so they're just having to waste it. They need to be able to store it. Lithium batteries are the most easy way of storing energy if you want it to be portable. Okay? And in transportation, Louisville's fairly small, like Binghamton, but if you go somewhere like San Francisco, New York City, I think you're going to find they're going to ban all internal combustion engines, probably within the next 5 or 10 years, certainly by 2030. And they're going to insist that you only use electric vehicles. The buses are going to be totally electrified, which will cut the CO2 down, but I think even more important, it will make it environmentally cleaner for everybody. So I think that's as big an issue as the climate change. And it's likely, certainly your children will not own a car. You'll pull out whatever the iPhone equivalent is, hit a button, and the car will drive itself up to your front door. You'll jump in, it'll drive you to wherever you want to go. You'll get out, and off it'll go and pick up the next person. So you won't need a garage. You won't have to worry about charging. That is coming. It's not ready yet. It'll work in California. I'm still not sure how it's going to work when the roads are totally snow-covered and it can't see anything, but we shall see. And the other big issue is that we have storage. We can make a cleaner, more resilient electric grid. In other words, it won't go down as much. And the goal, long-term goal, is your electric vehicles and your grid will be totally interconnected. So if there's a grid issue, they better get power from your car. When they got excess electricity, put it back in your car. If your house runs out of electricity, the cable comes down, you better plug your car in and power your house from your car. So the real challenge then is what we call the supply chain, where we're going to make these batteries, where we're going to get all the components from. Okay? Right now, everything goes through China. Everything, 90-some-odd%. That has to change. So there's a huge push in Europe, and Europe's got a master plan for the whole of Europe. They're going to mine in Scandinavia, use clean hydropower to process it, then make the batteries in, say, Germany or Poland, near where the auto companies are. Such is not the case in this country. We can do it. The challenge we have here is our, our political system changes at least every 4 years. It may change every 2 years. Europe has put a 10 to 20-year plan in place. This country really needs to do the same. And when I say this country, I'm really talking North America. We have to involve the Canadians in it because they have some of the minerals we need, they have the hydropower we need, and they can move faster maybe than the US can move. So we're touting that each region needs its own supply chain. And obviously Germany is seeing that now with gas coming from Russia. It's not a good idea to have everything coming from one place. But the scientists also now have to look at what's in the batteries. Could be what's in the solar cells, what's in the wind turbines. We have to take out of those systems any rare metals, any metals that are confined to one particular region of the world. Cobalt is an example for batteries. It mostly comes from the Congo with child labor, gets processed in China. We've cut it down now from 30% down to about 10%, and I expect it will go to 0% in the next few years. But that's something where the material scientists and the chemists have to work on it. We use graphite, and I'll show you a battery, what a battery is in a moment. We use a lot of graphite in there. That could be processed and made in this country. There's a lot of effort. Everybody sees now battery is going to be huge. They want to make them in this country, but right now they're being made in this country by Asian companies. And I think you're fortunate in the sense there are at least 3 Asian companies building facilities right in Kentucky right now. But the long-term goal, we want batteries made in America by Americans. So the goal will be, no, the Asian companies will be a bridge, but eventually we want to go the whole way. And this would be a good example of how you can switch from a coal economy to a cleaner one. There are a lot of challenges. Mining's messy. It's what we call, they use a carbothermal process. They'll use carbon to reduce the oxides to the metal. We've got to do more R&D and look at how can we use electrochemistry. Make clean electricity from, say, hydropower and use that to reduce the ores. And ideally, we do that at the mine so we don't have to ship the ores everywhere. We ship the finished materials. I want to make a little point, particularly for the younger folks. Think back. Why are you a chemist, a physicist, or an engineer? If you're a parent here, what got you involved in the area? And it's invariably a teacher in high school or a teacher in college. Think back to that person and thank them. No. This was my advisor at Oxford as an undergraduate and also as a graduate student. He was the one who got my enthusiasm going, got me involved, and really helped me go through the process. Unfortunately, he died about 2 weeks before I got the Nobel Prize, so he didn't know about it. But at Oxford, for your your bachelor's degree, you have to do a year of full-time research. And I did that at the time when there was a huge influx of money into science, because the Russians had launched Sputnik, and the Americans were going to catch up. So even though I was at Oxford, it was the US Air Force that paid for that research of mine. And then I went on to a doctorate funded by the gas industry. The gas industry was in a major flux at that time. When I got the scholarship, my scholarship was to come up with catalysts to convert what we call coal gas to natural gas. And I got that in June. In August, they struck natural gas in the North Sea. And they said, we don't care what you do. Do whatever you like, just send us a copy of the thesis at the end. So I grabbed that opportunity, and all you folks, grab every opportunity you can. Don't let it pass you by, okay? Because this is what can help you on. After that, I went to Stanford University. The previous fellow in our group had gone there. It looked good. And the key thing is the sun shone there. Unlike England and unlike Louisville the last few days. But no, it's a great place to go. As a scientist, you can travel. Take every opportunity to do it, learn what the rest of the world is all about. And then after Stanford, I then moved to the east to work what was then ESSO and turned into ExxonMobil eventually, to a brand new corporate research labs to work on anything except oil and chemicals. So that's where we got involved in alternative energy. And after that, in '88, that's 30 some odd years ago, I came back to academia and worked again on lithium batteries. So this is situation back in the 70s. I don't know whether you can see this guy here. I still have this clock in my basement. Things have changed a bit since then. These are single crystals we used for the batteries. We used single crystals for them. This is the original patent filed in the 1970s. And these are two of the products that Exxon made. They made a paperweight. This one still exists. It's built about 1976. We think it's still working. So a good lithium battery lasts forever. Beneath that is a large cell. It's about 6 inches by 4 inches an inch thick. We used at the EV show in Chicago in 1977. So Exxon was interested in making electric vehicles. Remember, there was no such thing as Walkmans, iPhones, any of those gadgets. No one had even dreamed about them at that time. Those all came much later. So it's electric vehicles that drove this business. And if you want to see those batteries, you can find 2 of them. After we got the Nobel Prize, you have to take something to the museum there. So Bob Hamlin, who ran the manufacturing facility at Exxon, and myself, we looked in that basement and managed to find 2 cells. That's these 2 here, plus the original sales brochure. So those now sit in Stockholm, if you ever get a chance to go over there. But this is now where we stand. You saw those little batteries to begin with. If you look at transportation, these are the typical vehicles you see, a small 2-seater. These 2 big trucks that I had the opportunity of driving, and this is my wife driving this one. Electric bus in Germany. This is a bus built by BAE Systems, or I should say electrified by them. This is done in Binghamton. This is a Raymond forklift truck. Raymond is a subsidiary of Toyota. This is also in the Binghamton area. And this is a beautiful BMW if you have $100,000 to spend. Okay. So this is what is actually happening in electric vehicles. No extrapolation here. This is the last few years. This is where we stand right now. So it's increasing exponentially, and it will keep doing this if we have sufficient materials in the supply chain. This means the actual materials to make the batteries and all the semiconductors and chips that enable them to be used. But this is the anticipation. That's why there's so much interest in the area. The other area where lithium-ion batteries are used are in the International Space Station. So I and 2 of the physics Nobel laureates had a chance whilst in Stockholm to talk to these 2 astronauts. This lady is from the state of Maine. Her mother was Swedish, and he is from Italy. And they're just finishing changing all the batteries in the space station from nickel metal hydride to lithium-ion. They were very happy. They weighed half as much. They took up half the volume, and they were going to last twice as long. And clearly in space, they weighed nothing anyway, so it was easy, but they're just finished doing that. And what's amazing, we talked live to them. There was absolutely no delay. We talked, and they responded straight away. And that link was from Stockholm to Houston and up to the space shuttle. So let's move on to climate change and renewable energy. There's a big advantage to renewable energy. First, it's lower cost to build a power plant now than coal. Once you've built it, the wind or the sun doesn't cost you anything, and you don't have to ship it in, like oil or gas or anything else. And then in bad weather, it doesn't freeze. So it should be there no matter what. But it is intermittent, so we need storage. And clearly one of the areas where there's a huge effort right now is for solar energy. But let's look at different ways of storing energy, and these are really for different purposes. By far the largest way of storing energy is pumped hydro. And I show you a scheme here. This is one in New York State. There are a huge number in the Tennessee Valley Authority, in Pennsylvania, and many other states. So at nighttime, you pump water up to upper reservoir. In the daytime, if you're going to use it, you let it come down and convert it back to electricity. They're mostly used for storing energy in spring and fall, where you don't use much energy. And then you use it, say, in the middle of the winter or the middle of the summer when you need it. So it's long-term storage. And a huge number of these throughout the United States. It's not clear we're going to be allowed to build anymore because of environmental concerns. So that means then that batteries, we're going from chemical to electrical energy, are the most common, extremely flexible. So you can put a little battery in your watch, or you can put them in the huge facilities, gigawatt hour facilities. So that's the big advantage of them. You can switch them on very fast in milliseconds. This system takes, they think, about 2 minutes to switch on. Once the New York Power Authority says we need some more energy, it takes about 2 minutes. But batteries can fill in that 2 minutes and obviously go much longer. Another system that's been looked at is flywheels, where it's kinetic to electrical energy. You're going to find very few of these around. There's one in Albany, New York. They got it going. The company went bankrupt. Another company took over the facility. They didn't have the capital spending involved. They're making money now. This is mostly used for smoothing out, so the grid is smooth. It doesn't really store energy for any length of period. But you're also not going to see these used in small applications because they're like a huge hand grenade. If something goes wrong, they fall apart, you've got a real problem on your hand. So this is what people are using today. So we've got this case, you've got solar energy in California. They're storing it in this facility in Moss Landing, which is about 1.5 hours south of San Francisco on the coast. It's built in an old gas-fired power plant. The advantage of this, all the grid infrastructure is already there, so you don't have to spend any money connecting it to the grid, it's there. This particular one, as of today, is 1.6 gigawatt hours. This is a factor of 4 larger than any other facility in the world. And they've got permission to go to 5 to 6 gigawatt hours. And if you read Bloomberg, I think it was yesterday's Green Edition, they say this is only about 1% of what California actually needs today. The last day of April, they threw away about half the solar energy they generated because they couldn't use it. If they had storage, they could. And up here, this is a wind farm. This is in West Virginia. This, I think, is about 32 megawatt hours. Again, it's used for smoothing it. If you look at any of these facilities, you look at the wind, you think it's blowing or the sun is steady. It's going up and down like a yo-yo, second to second. So you have to smooth that energy before it goes to the grid. And that's what these batteries are doing. And also, they can shift the energy for about 6 hours. Okay, let's get back to the batteries. And some of you saw this yesterday. Just as a reminder, if you have a lithium-ion battery, you have no lithium in it, hopefully. If you have lithium in it, on plating you'll form dendrites. This will short the battery out, and this is built by a Canadian company and used by AT&T. So there are no batteries in the US that use lithium metal anymore. So we store the lithium inside another compound, and specifically we store it inside graphite. I'll show you that in a second. And here is a picture of a typical lithium-ion battery. You have 2 electrodes. You store the lithium in both electrodes. When it's fully charged, all the lithium's in this graphite side. When it's fully discharged, it's all in this side. When you discharge it, these ions go through the electrolyte. The electrons go through the external circuit, creating the work you want. Okay, so very simple concept. If you look up this word intercalation, you'll see it related to February 29th or to January and August in the calendar, when these were intercalated in the calendar and taken back out. Chemically, it means a totally reversible reaction. And that's the only reason why you can cycle batteries thousands of times. So that's the 3 of us. The 3 of us got the prize, but there are many others involved in making this happen. But I'll show you later. No one person can make major inventions. No one discipline can make major inventions. And normally no one country can do it. So it involves a lot of activities by a lot of people. But This is Akira Yoshino, John Goodenough, and we'll be going to John's 100th birthday symposium in July this year. So long as he's still alive, I'm still mid-career. Okay. And we each played a role in making the lithium-ion battery a commercially successful product. So at Exxon, we start out with pure lithium. This, as I showed before, can form dendrites. So we switched to a lithium aluminum alloy. That works just for a little bit. Then Akira Yoshino switched to graphitic carbon, and that's what's shown here. But this carbon takes up half the volume of the cell, so it has to go if we want to make better cells. Okay? So we're looking at things like tin or silicon itself, and we have a major project going all the way back to lithium. And in the middle here, the folks who made this really commercially viable was Sony. They invested engineering money for about 10 years, whilst no American company and no European company were willing to do it. Sony is what they call a vertically integrated company. So they had things like the Walkman or the predecessor to it. They wanted to make everything that went into that, including the battery. So they basically bought this technology. On the cathode side, we start out with one layered compound like this. John Goodenough switched to a second one. I already mentioned cobalt's expensive and child labor issues, so a lot of cobalt is replaced by nickel and manganese, but it's still a layered compound. Then we have these phosphate materials, which are also good materials in here. So there's a lot of science going on, studies looking at different materials for batteries. And I think you all recognize this little guy. So again, don't worry about these numbers in here at all. Forget all the numbers. All you need to see is in that red circle, it goes from 11% to 25%. This is the amount of energy on the volumetric basis you get in a commercial cell relative to the theoretical value. This is the weight. We've got to be able to do better. That's why there's a lot of research going in to make the batteries better than they are today. Part of that, we have to get that graphite out. You have to use more lithium, and we have to be smart as to how we make these cells. So a challenge we have, as I said, we started out with lithium cobalt oxide after the sulfides. Cobalt's too expensive. We want more and more energy. Now you want all your phones to last 2 or 3 days. You want to be able to talk and run movies on the phones and not have them run out on you. So you want more energy. So what you want to do is really replace the cobalt with these other elements. And to get more energy out of here, you want more and more nickel, it turns out. So you want a high amount of nickel. And this just shows you what happens if you put a high amount of nickel in here. This is more nickel. Turns out this is more energy. But this means these materials are not very stable. So they're liable to, if things go wrong, catch fire much quicker than something with no nickel in it. So you have a trade-off now between safety and energy. And this is, you have this in essentially every product. So people say, are batteries inherently unsafe? My comment back is every energy source is inherently unsafe. So ask yourself today, if you were to invent the internal combustion engine, would you be allowed to put 20 gallons of a flammable liquid under the back seat, then put your child's seat on top of it, then put your 2-year-old toddler on top of that? If you tried to get that approved by the feds, I don't think it would happen. We've got just used to running with that risk. So what we're trying to do right now is increase the nickel content, but understand all these reactions so we can make them safer. And I don't want to go through the details in here, except say we are involved in a large consortium run by Department of Energy, organized by Pacific Northwest National Lab, and our goal is to get from 250 to 500 watt-hours per kilogram. This is not a good unit for cars. Cars, you're more interested in the volume, how much space it takes up. But anything the Department of Energy does has to be sold to Congress. Congress understands the word 500. Because just up the street from here, you've got the Indianapolis 500. So they basically sold it on that basis to Congress. Now, this is a program where we're going to get to 500. So as we worked on this, you can see we're going further and further to the right, and we're up to 600 cycles. This is 350. We can get to 400, and with some changes in chemistry, we can get even further. But this work was done by an ex-student of mine, Jay Xiao, who's now at Pacific Northwest National Lab. She leads the effort there. So if you're thinking of a career and you're not sure, should I go academia, should I go industry, national labs are a good compromise in between. Because you go to a national lab, it's much easier to switch to one of the other two. Okay. And I won't go into much of this except of these. This is what we call the morphology of these materials. This is the shape of them all. By having these meatballs, they pack well together so we can make a very dense electrode. So I mentioned earlier that the lithium-ion phosphates that John Goodenough discovered, they're safer. The oxygen is held in the phosphate group. They're less likely to catch fire, but they have a much lower energy density. And maybe, let me see if I can go backwards. So look here, the energy density of these phosphates. Here's the theoretical, here's the actual. You see there are about half of these numbers here. So our goal was to see whether we couldn't get it higher. And the idea was if we can get to 200 with one lithium, maybe we put a second lithium in, we can double it. So our goal was, can we insert two of these ions into a lattice without destroying that lattice? And clearly, if we hadn't succeeded, I wouldn't be talking about it. But we got a prize from the White House. I should say this was from the Trump White House. Trump supported battery research, quite readily. It's even higher now, but it was very good in those days. And we got a prize from the Department of Energy. This is one of the undersecretaries, one of my students who's now at Argonne National Lab, and one of Claire Gray's students in Cambridge, England, who is now back in England at Imperial College in a faculty position. But to make these kind of things happen, you need a large team. So the days of individuals working by themselves, I don't want to say it's gone totally, but if you want to make a real impact, it's essentially gone. If you want to make an impact, you need a group of people with very different skills. So we have people who do theory, people who can make things, people who can measure things, and people who can use these big machines in national labs, the synchrotrons, to actually characterize where all the atoms are. So this is a list of some of our team members at the bottom here. We had this program for about 10 years. So we had Claire Gray did nuclear magnetic resonance. She's probably the world leader for solids. Rutgers looked at some of the systems. San Diego did theory here. Stony Brook was doing the synchrotron work, and University of Michigan was doing modeling of the entire battery. So you notice a lot of theoretical and modeling work in here. And some of these theoreticians guided the experimentalists. So if you had 10 different compounds you might look at, you would ask the theoreticians, how would you prioritize these? No, it doesn't always work. No, they'll say this lithium compound will work great. Then you look in your tables as a chemist. You say, if I take this lithium out, then what's left is a gas. It's not going to work. So you have to still use chemical intuition. But things work out well. I think I showed you this yesterday. After many years, we made these little cuboids. These are 100 to 200 nanometers in size. Phosphates are electronic insulators. Remember, in a battery, you want the electrons, so the electrons have to get in and out. So you have to make it conducting. That gets tough. But here's the data we got. The black, I'm not going to go into the detail here. Just look at the black curve. Here's lithium going in, lithium coming back out. The purple one is the 50th cycle. The black is the first, so it's behaving better on the 50th cycle than the first. So we now know that we can put two lithium ions into a structure without wrecking that structure, and we're pursuing this now with some South Korean funding. So again, you see we're going to Asia to get help in doing this, and this is still common in this field. So I want to make a point here that I mentioned earlier. You can't do everything by yourself, even in Kentucky. No. You need help from others. So if we look at this particular invention, science is very much interdisciplinary. The exciting areas of science are not inside chemistry, inside physics, inside biology. It's at the boundaries of the present disciplines. So if we look at chemistry, the exciting areas are between chemistry, biology, and medicine, or between chemistry, physics, and material science. And that's where most of the action, I think, if we look at the faculty here, you can place most of them in one of those two boxes. Okay. So to put that in perspective, I'm a chemist. John Goodenough is a physicist. Akira Yoshino was an engineer. If you read the literature, pick up any journal these days, you'll see every paper probably comes from a different country. We read those papers. We don't just rely on American or European ones. And this used to be the case before we had instant communication. You didn't get the journal if it's published in America. It would take 2 weeks to get to Europe. It took 3 months to get to Australia. So if we look back and look at the most famous Australian scientists, they in fact left Australia when they were young, came to the US or to Europe, then once they got the equivalent of tenure, they would go back. So it was tough in those days. Nowadays, you can go on the internet and look up the journal. Quite often you can read the journal before it's fully published. So it's a huge difference. So again, science is international. I say it knows no boundaries. I want to emphasize, as you can tell, I was born in the UK. I'm an American now, but I made my inventions in America. John Goodenough was born in Germany of American parents. He's an American, but he made his inventions in England at Oxford. And Akira Yoshino is an engineer, and he made his inventions in Japan. So it took 3 continents to make this a success. Without Japan and their willingness to put a huge amount of engineering and development in it, it's not clear when this would have been commercialized successfully. A number of companies tried it in the US, a number went bankrupt, and a number had fires and other issues, but it really needed the Asian push there. I've already mentioned this plenty of times. Energy storage is going to help renewable energy. It's clearly going to make a cleaner, more resilient grid for all of us. It's going to make our cars and trucks cleaner. And I should point out, this is what I had to give speech. I got, I think, 3 or 4 minutes to give this speech. At the banquet, each Nobel group has to give a speech. John Goodenough is not able to climb stairs anymore, so he couldn't do it. Akira, Japanese, he said, I'm not doing it. Stan, you're doing it. So I had to give this quick speech. And other thing I mentioned in this speech, because we're international, we have to understand the cultures of other people. We have to understand better how they think and not just try to push over on them the American way of doing things. They don't do things the American way, particularly in Asia. Even in Europe, they don't do things as quickly as Americans do. No, and they check bases much more often. So we have to understand the cultures. And all of you in the audience have to persuade all your friends that facts do matter. Despite what some politicians may think, we have to convince them, no, climate warming is real. Anybody who goes out in the country will see that. And I don't understand why Trump doesn't see it, because the water is getting higher and higher around his house in Florida. It's only a matter of time before it goes in there. I got a few more slides I think I want to show you. Just the future, when we're talking about greener, safer energy, the batteries aren't going to really change that much. They're made by the billions. It's going to take a lot of effort to change it. For those of you in engineering, we need cleaner, more sustainable ways of making things. We have to stop throwing things away. And this particularly means all your batteries in your phones and other gadgets. They've got a lot of cobalt in it. I suspect in this state, just like in New York, some of the garbage dumps are probably richer in cobalt than the mines in the Congo. So we have to recycle everything. If you've got any device you want to get rid of, just remember, there are several stores who will take it with no questions asked. Best Buy is probably the best one of those to go to. You can take any old battery, any old phone, they'll just take it and send it for recycling. So what we are hoping to do is make things more sustainable. We've got to reduce the amount of energy that's needed to produce a kilowatt-hour battery. A lot of this is in transportation. As I said, all these materials tend to go through China, then back to the car manufacturer or the grid. Some calculations show some of these materials go 50,000 miles, which is crazy. There's no need for that. No, we've got all the stuff we need in the Americas. We could easily do it within this continent. We've got to come up with new technologies so we can leapfrog the Asians. And some of the semiconductor companies are trying to get involved here to make batteries using what we call clean, dry methods, so we don't involve toxic organic chemicals. We've got to come up with clean mining. We need clean recycling, not heat it and beat it. So we've got to try to take the material off and directly reuse it rather than burn it. And with this, we'll get it more sustainable. The thinking in 10 or 15 years, most of the lithium and cobalt we all need for new batteries will come from recycling of old cars and old systems. And that's the only way in North America we'll make it, I think, sustainable. And what we're trying to do locally, we're trying to build a capability in Endicott, which is just across the street from the university in Binghamton. This is the old IBM facility. IBM started out in the Binghamton area. About 10, 12 years ago, they decided that they're out of manufacturing. They closed everything down. So there's a huge manufacturing expertise there. So we hope to enable things to happen there. And when our politicians come to visit us, like Senator Schumer did about 10 days ago, we and he emphasized we've got to get back to it's made in America, not made in somewhere else. Okay? And we can see this is needed for security. And we really need a clean ecosystem. I say you're beginning to do that here. That's great, but it has to keep going on forward. So this is really the issue today. We come up with great ideas in academia, startups, industry. We can make small cells, we can test small cells. But if you want 1,000 of these cells, then they all go to Asia. They make the cells, then they provide these for the electronics grid, military vehicles. Clearly, the Department of Defense is not happy about this. They want to have everything made here. And I just show you two examples. These are forklift trucks. These are made by Raymond, which is a Toyota subsidiary next to Binghamton. And here are buses, which are electrified by BAE Systems. Again, they get their batteries from South Korea. Raymond, fortunately, they're transitioning over to Canadian-based batteries, and the Canadian company said they're planning to move to New York State shortly, so we'll get some infrastructure and manufacturing right there. So this is what the present situation is. What we're proposing is to build what we call a battery in New York, which will have a large manufacturing effort where manufacturers can come in with their new techniques, ideas. Most of the battery equipment could be made in the United States. The companies just don't know that they could do it. So we're working with present manufacturers to say, no, you can make this part of it, you can make that part. A few companies are switching over. So these are all manufacturing companies. They can easily do this. They need a bit of investment. The other thing we're doing is making a production line to make full-size cells, which allow testing of prototypes. Now, if you're a Ford, you're not going to say, well, we've tested 10 cells. They look good. They're going to want tests on, say, 1,000 cells minimum before they commit. They can't do that within the US at the moment. And this is what our program is. I won't go into that or into this. I just want to finish this up. I know there's some younger folks in the audience here. The Nobel ceremony is very much a family affair. So each Nobel laureate's allowed to take, I think, 12 to 14 people with them. No, Nobel doesn't pay for them to go, so you pay for this. But no, this is my family, both from the US, from the UK, and you'll notice they're very much multicultural, not all lily white Europeans. So, and doesn't matter whether you're 9 years old, as my grandson was, or myself at somewhat senior age, you all have to get dressed up appropriately, and the men get it easy. There are special tailors there that rent you everything. You just tell them beforehand, we've got somebody of this age or that age, and say, come on over and we'll dress them up. The women have to get their own dresses, outfits. And if you're going to the big banquet, you need one dress. If you then go to the palace for the smaller one, the women want a second dress. So it's somewhat like I expect the Derby tomorrow. They each have to get very dressed up for these events, so it's much easier. So this is, after the awards ceremony, this is my wife making sure I'm dressed appropriately. And yes, there is a red carpet, and this is the paparazzi being held back by some of these guards there. And my wife's pointing out the Volvo that's waiting for us out there to take us to the ceremony. So the whole thing lasts about 10 days. We have a driver assigned to us, plus a Volvo car with Nobel insignia on the outside of it for that 10 days. Plus, lady here, I think you can see her in the back here, she's from their equivalent of the Foreign Office, who stays with us the entire time. So we have to give lectures to K through 12 schools, one at the higher level, one at the lower level. We have to go, in my case, to the British Embassy and the US Embassy for events there, and give talks at some universities. Plus, BBC puts on a 1-hour program for each discipline, chemistry, physics, and so on. And for 1 hour, it takes about 3 hours of recording, because they're a professional moderator. No, it does the weekly programs just like in the US. She'll start, then the director will say, you've got a hair sticking up here, let's do that over again. So we start from the beginning again. But all those activities, this is when we get the award. And I have to point out this one, I grumbled to my president. He put my name above my lab, and this is my wife again. And I tell him, you put this here as I'm getting older so I can find where my lab is. But I will stop there. No, it was an exciting period of my life. And if you're a scientist, you can aspire to such things. But even if you don't get to that level, you can travel around. Key thing I want to remind, doesn't matter whether you're, I think some of us are 9-year-olds in the audience, up to 80-plus-year-olds. You've got to do something that excites you. Do not do it for the money. And remember what Einstein said. Imagination is more important than facts. If you don't imagine and dream, you won't make the big breakthroughs. So I will stop there, and if you've got any questions, I'll try to answer them. Thank you very much.
The microphone, please.
So if you have any questions.
On one of your last slides, there was a bullet point that said lithium systems will dominate for the next 5 or 10 years. Does that mean that there is another generation or a paradigm of batteries that's on the way?
There's a lot of effort on what we call flow batteries, which will be lower cost, much lower energy density, but maybe better for grid storage. And so in the long run, what the utilities are looking for is lifetime cost. And with flow batteries, you can separate the power from the energy storage, so they're more flexible. but they're far too expensive today. Any new battery system coming on the market is going to have to find a niche market where they can make money from day one. Because lithium-ion batteries today are made by the billions, so it's very low-cost manufacturing.
I'll admit my ignorance. Could you briefly explain what a flow battery is?
Yeah, you'll have two tanks of reactants, so instead of having solid lithium and, say, solid cobalt oxide, you might have zinc and maybe water on one side. You'll circulate the zinc and the water on different sides of the separator, and they will react there, forming zinc oxide. There are vanadium analogs of that. When it's discharged, then you just recycle them, and you can recycle them externally of the battery itself, if you want to.
Thank you.
My father is a solar installer in Albany, New York, actually. And he does mostly residential systems, but he also installed the system on the governor's mansion and a couple of other very large installations. What he's found with government incentives and such is that the incentives are currently set up to discourage having a lot of battery storage for solar systems in New York and in other states around the country. So do you envision this changing to become something that residential individuals have as a part of their energy system, private energy grid, or only large systems like you showed us in California?
This is very state dependent, and it depends on what they call the ISO systems for each state, how they control it, and it depends on how the financial structure of the utilities are set up. How do the utilities make money? And the states have to define whether a battery is a generation or past-the-meter storage. If it's generation, they can make money on the large scale. If it's on your side of the meter, they don't get involved in that. So we're trying, particularly in New York State, to allow the utilities to make money no matter where it is. And that's the only way, it's the same with if you're going to use reservoirs or anything else. You've got to be totally flexible these days. But those studies are going on in New York State right now at the statewide level. And our facilities going in just north of Binghamton. They're putting a large storage facility in next to some substations. And they're going to install these and power them up at night, then discharge them when the power is needed in the daytime. There are some near Saratoga Springs where they're making money already. So they can clearly make money. California is a special case where the utilities are putting this large grid storage in from solar because they're getting more solar than they can use at the moment. I think the last day of April, they got 99.8% of the electricity generated at noontime was renewable. They weren't using any other source of fuels. They would like to do that all the time, but they don't have enough storage to do it. But California is clearly going to central storage. California, it all depends. A lot of states, your solar, you can, how do I put it, reverse your meter if you give it back to the grid. Some states you can't do that. If they don't allow that, then you want your own storage. It's much cheaper if you can just feed it, reverse it back to the grid. You don't invest in the storage yourself then. But there's a lot of effort in New York to put batteries with solar systems alone and batteries alone. It all depends on the locality and the rules they've set up. Basically, this is an issue with, can I say, the political system in this country. It's not only every state has different rules, every area within the state also has different rules, which makes it very difficult.
Yep, in the back. Very interesting talk again today. I was just wondering if you would speculate on other modes of transportation besides cars and trucks. So rail, obviously, can be electrified using existing technology, but what about ocean-going ships and airplanes?
Yeah, I didn't show an airplane this afternoon. I showed one this morning. The issue with airplanes is you can't really use batteries for anything beyond, say, 100, 150 miles. You'll be carrying more batteries than you carrying cargo or people. It's the same with the big 16-wheelers. If you're going 100 miles, that's fine, but if you're going much further, you're then carrying more batteries. So on the big trucks, they're talking about hydrogen fuel cells with a battery. For planes, they're talking about short hauls. Maybe, you know, if you're looking at, say, something like the Seattle region, from Seattle to all the little islands around there. Huge effort now on small planes, vertical takeoffs for rescue missions, where you can take supplies out if someone's got stuck in a canyon, take it out to the first responders to get it there. I don't think you're not going to have an electric plane running from, let's say, from here to New York City or from here to London. It's just not going to happen. What about ships? Ships is going to be the same issue. You've got to carry that energy with you. By far the most dense form of energy are liquid fuels. Hydrogen might be feasible, but I think a lot of governments, you know, we're seeing what's happening in Russia and Ukraine, a lot of governments will be very upset if you had a big ship full of hydrogen and you had a terrorist somewhere around with one of these little rockets, it can blow the whole thing up. So I think there's issues there. But things like hydrogen will be used for 16-wheelers and trucks of that nature. And they'll be used for fleets.
So where does the grid in the United States is apparently quite inefficient. 20 to 30% of the energy is thrown away. So it seems like we're ripe to redo the grid. What do you see? How would we design a grid to accommodate batteries and energy storage better?
I would say California is doing that already. The issue is the grid in the United States is very old. It was probably one of the earliest grids built in the world. It's old now, it needs replacing. The question people say, do you want DC or AC on the grid? Which is the most efficient. It's AC now that has bigger losses. So I think, and the other issue that we're talking about is now, we want a big grid, but do we want microgrids attached to the big grid? So for example, Louisville could be separate from I think they call it the Eastern grid. So if something went wrong, let's say in Lexington, it wouldn't cut the power off to you, you could still keep going. So they want to make it so each region is maybe a little more self-sustained. But no, then you've got states like Texas that refuse to be on the national grid. They have their own private grid, and you saw what happened when they had this freeze, was it last year? Yeah. No one else could really help them. But no, we do need a national policy to upgrade the entire grid. And this is a big problem for wind farms. It turns out the present grid is not capable of taking the amount of energy some of these wind farms can generate.
So in the beginning of the lecture, you said that you think vehicle to grid, using the car as a battery backup for the grid would be commonplace. But currently, the biggest thing that's retiring old electric vehicles like Nissan Leafs is battery degradation. So do you think that that's going to be an issue, getting people to be willing to use their batteries to back up the grid when it's going to degrade the battery faster? There's 2 points here. One is you'll void your warranty if you do it today, because they're not made for that. Nissan Leaf is definitely not made for doing that. Nissan Leaf uses air cooling of the battery, not liquid cooling, which everybody else uses. So if you try to buy a Nissan Leaf in Arizona, you will not be able to buy one. It's the same issue. You've got your laptop computer, it starts getting warm, it turns on its fan, the temperature outside is 120, it gets hotter and hotter instead of cooler. So Nissan Leaf does not work in hot climates, and whatever you use, you're going to need extremely good thermal management of the battery to make sure it does not get damaged. And lithium batteries are just like you. They want to be 70 degrees Fahrenheit, plus or minus maybe 10. In extreme conditions, it can go a bit further. But if you look at the large storage units on the grid, they are not 90% efficient, which most batteries are. They're about 70%, because 20% of the energy is used to air condition those large containers. And my wife and I can attest that we went to a container farm near Saratoga Springs. It was about 95 degrees outside. We were looking at this and said, how soon can we get inside? They open the door and you go inside. It's a nice 70 degrees Fahrenheit inside. So, no, if we can come up with better batteries that can operate over a wider temperature range, it will solve a lot of those problems as well. But right now with these organic electrolytes, they're not stable and they will degrade very rapidly at elevated temperatures.
This may be related, but you have two different markets for these batteries. The stationary market, which can be charged slowly and then released slowly, and then the portable market, such as cars and portable phones and things like that, in which there's been a lot of effort in the last several years to increase the recharge rate of these things so that you make it about the same as filling up your gas tank or things like that, which I assume leads to part of the degradation problem that you're facing. Is the technology solved for that and it just has not been implemented, or is there still a lot of research to prevent that degradation just on rapid charging?
They will naturally degrade on rapid charging. You're forcing a chemical reaction to happen. The other key thing is people don't realize you can do a back of the envelope calculation. If you got a 100 kilowatt hour battery in your car like a Tesla, if you want to charge it up in 5 minutes, you can calculate how many hundreds of amps at how many thousand volts you've got to put through that cable. It means you've got to have much thicker cables in the car, much bigger buzz bars. They're heavier, they're going to cost a lot more money. And so most people say, we don't really want fast charging. We can fast charge now maybe once a month, but not every day. Your service stations definitely do not want fast charging. They want you to plug your charger in, take 20, 30 minutes, you can go to the restroom, then you can go and get your hamburger, buy a soda, and make some money for them. But no, a lot of people worry about fast charging. The only really reason you need fast charging is probably if you're a commercial operator, where you're running continuously. But any of us, if you've got a car that will drive, say, 300 miles, if you drive, let's say, average 60 miles an hour, that's 5 hours in the car. You're going to want to get out and stretch for 30 minutes, I suspect. So I think that fast charging is getting a bit overemphasized. The military clearly would like fast charging, but I think for most of us, it's probably not necessary, and it will definitely degrade the battery.
If we don't have any more questions, let's thank Professor Whittingham for having a wonderful talk. Thank you everyone for being here.